Okay, this is going to be our first video in our series on sources of magnetic fields. So this is chapter 28 from the textbook, and I'll get right into it here. So in the last chapter we studied how magnetic fields exert forces on moving charges and on current carrying conductors. In this chapter we're going to focus on the sources of those magnetic fields. So we're going to focus on what's producing these magnetic fields. We're going to see that it's moving charge that generates these magnetic fields. Okay, and so we're going to start off with section 28.1 from the text here, and basically everything in this video maps directly to section 28.1. So so from experiment we can see that the magnitude of our magnetic field for a point charge, so the magnitude of the magnetic field generated by a point charge of charge Q moving with some speed v at some field point that we're interested in measuring this magnetic field, which we're going to call P, is given by the expression that we see here. Okay, so I just kind of write it straight down. This is an expression that you could kind of logically argue and build up to some degree, but at some point you actually need experiment and to do the measurement to be able to get this leading factor here. We could argue that, well, this thing is going to have to depend on Q to some degree, and it's going to have to depend on R, the distance between these between the source and the field point. And because we know magnetic fields are generated by moving charge, it'll probably depend on V, but the rest of it you kind of have to get from experiment. So rather than going through the whole discussion, I just write it down directly. This is the magnitude of the magnetic field at some field point P generated by a moving charge at a source point. Okay, and we're going to sort of see how these relate in the diagram below, but I'll say a few more things about the equation here. As I mentioned, R is the distance from the source point to our field point. Phi is the angle between our velocity v and the vector drawn from the source point to our field point. And this mu naught is a new constant, which we're going to call the magnetic constant. I'm going to give you the value for that down below on the next page, but we now pick up a new constant, very similar in many ways to our electric constant, which we saw in chapter 21, and we're going to see that they are actually intimately sort of related, and they tell us some pretty profound stuff about the way that electricity and magnetism and then even light relate to each other, and I'll just mention that really quickly down at the bottom. If we make it to future chapters, if we make it all the way to chapter 32, we're actually going to explore that relationship a little bit more deeply. Okay, so this is the magnitude of our magnetic field, but the direction of our magnetic field at this point P can be given by another right-hand rule. So let's take a look at how that's going to work. So we can imagine here that we have some positively charged particle moving in this direction here along the sort of interface between these two planes that are drawn here, and we can see its velocity is drawn in here. This is the velocity v, and so this is going to be our source point, right? This is our positive charge. This is our source point. And let's say we're interested in some measurement of the magnetic field at a point P out here. Okay, so we have our vector drawn between our source point and our field point. Our vector is R here, and it points in the R hat direction. And if we take a look at the diagram here, we can see that if we use our right hand and we line our right hand up in the direction, well, in such a direction that our thumb is pointing in the direction of the velocity, well, then our fingers of our right hand are going to curl in the direction of the magnetic field. Okay, so we can kind of see that sort of all playing out here. So at the point P, if we think about the right hand that's drawn on here, the fingers curl in the direction of B. Let's say we were interested in some point over here, right? Let's say we're interested in some point over here. Well, then the fingers on our right hand still curl sort of downward here, so you can see it kind of curling in this direction. If we were to look at the the particle sort of going away from us, if we were to stand here and look at this thing, we would end up with this picture here. We see that the charged particle is heading into the page here, right, sort of away from us, and the magnetic field points in these directions as we sort of look down the barrel of this thing as it's going away from us, right? And so this sort of view of the charge going away from us and the magnetic field here, this is really what the magnetic field lines would look like too, right? So for a moving charge, we end up with magnetic field lines that look like this, where if we remember back when we talked about electric field lines, well, our electric field would look like lines just coming directly off of this charge, right? But when moving, we get this magnetic field that looks like the blue lines that we see here. Okay. So you can probably guess by looking at this expression here, we have this v, and we have a sine phi in this case, and we're talking about this thing pointing in a direction that somehow relates to r and v. So you can imagine that we're going to come up with an expression that encapsulates both of these into a vector expression, and that's exactly what we're doing here. We can take this information about the magnitude of the magnetic field and about our direction of the magnetic field, which we get from our right-hand rule, and build it all into a single vector expression, right? And that's exactly what we have here, expression 28.2 from the text. This is really the sort of key expression that we're going to want to remember from this section, and it's really how we're going to calculate the magnetic field outside of a moving charge. Okay, so let's take a second here to look at it. We have the magnetic field due to a point charge with a constant velocity. That's our B field vector here. We have the magnetic constant over 4 pi, the charge of the particle that's moving. This is the velocity of the particle that's moving, and we cross that into the unit vector, which we can see on the diagram here. This is the unit vector defined by the vector that points from our source to our field point. Okay, so r is this distance between the two, and r hat is that direction. Okay, so sometimes, like in the case of the electric field, we might find it more useful to write this r hat in terms of just the r vector, so we don't have to pull out the unit vector nature of it. Let's say we know what r is. We don't want to have to find r hat or like it's basically an extra step, right? We can easily find the magnitude of r, but then we don't have to find r hat. We just have r. And remember that this is because we can write r hat as r over r, right? So we're just replacing r hat here with an r over r. We end up with r on top, but we pick up an extra factor of the magnitude of r in the basement here. So sometimes it's more useful to use it this way. Both ways work depending on the information you have in the problem. Okay. So like I mentioned, the magnetic field lines that we saw up here, I mean, this is really originally designed just to show us the direction of our magnetic field, but really they show us the magnetic field lines as well, right? So we can think of the magnetic field lines in that way. We want to remember that the SI units for our magnetic field are given in Tesla again. So we have Tesla as our units for the magnetic field, and our SI units for mu naught, this new magnetic constant, are going to be Tesla meters over amps. Okay, and it takes on the numeric value that we see here. So mu naught is going to be equal to this value here. I think it's to like 8 sig figs or something, or 8 decimal places at least. So we're going to have 1.25663706 times 10 to the negative 6. Okay, but this is very close if you do the calculation to basically just 4 pi times 10 to the negative 7, which is kind of nice because whenever you see this collection of units or of variables, you can kind of just replace it for 10 to the negative 7, right? Because you'd have 10 to the negative 7 times 4 pi on the top, but that 4 pi is going to cancel with the 4 pi on the bottom, and the whole thing just works out to be 10 to the negative 7. Okay, so that's how we'll kind of use it in the future. I'll often write it like this, and then we can sort of go back and forth as we calculate, right? One last thing I wanted to say before we move into an example from this section and then move on, is that I mentioned this sort of relationship between epsilon naught and mu naught. So let's remember from our work in chapter 21 that our electric constant epsilon naught takes this value here, so 8.854 times 10 to the negative 12 coulomb squared per Newton meter squared. Okay. If we combine them, and I know right now we have no good reason to want to combine them, but let's say we did. Let's say we're just playing around with them. If we combined epsilon naught and mu naught in this combination that we see here, if we multiply epsilon naught times mu naught, take the square root of that, and then take its reciprocal, we're going to find this value here, right? 2.998 times 10 to the 8, and the units, if we multiply through all these units, are going to work out to be meters per second, which is kind of an interesting coincidence at this point. And if we think about this, this is really c, right? This is the speed of light in a vacuum. We don't really know why this is the case. I mean, we know, physicists know why this is the case, but right now at this point in the course, we're not sure that there's a sort of good reason to motivate why this happens. But it's an interesting coincidence, right? The relationship between the electric constant, the magnetic constant, and the speed of light is hinting at a sort of much deeper underlying set of things that's going on that suggests this really intimate connection between electricity, magnetism, and the nature of light. Okay, and this is really sort of one of the punchlines of the course. If we have enough time, and if we make it to chapter 32 in the time that we have, we're going to explore this relationship further. But this is definitely something we want to remember, that there's a connection between our electric constant, our magnetic constant, and if you write them in this way, basically what you end up seeing is that epsilon naught times mu naught is equal to 1 over c squared. If you kind of square both sides and just isolate these terms on their own, right? So this is kind of a relationship we want to keep in the back of our heads. So back more to sort of the physics that we're talking about in this chapter. If we take a look at an example from the chapter, we're going to take a look at 28.1 here. It's the only one they do sort of in full detail in this chapter. We're going to take a look at it, and we're going to see sort of how these forces and, well, first how the magnetic field is going to be generated by these moving charges, and then how these forces are going to relate to each other, the resulting forces that we're going to see here. So let's take a look at the example. We have 2 protons moving parallel to the x-axis in opposite directions here. So we have this diagram here. We have one proton moving in this direction. We call that negative v is the velocity for its motion. And then we have v moving off in the positive x direction here. And they're moving with the same magnitude of the velocity, right? So v and v both here are the same magnitude. We do need for this v to be small compared to the speed of light, right? So if v is small compared to the speed of light, our calculation is fine. If v was much larger, and we start creeping up on the speed of light, some significant fraction of the speed of light, we'd have to do a different calculation. We'd have to take into account relativistic effects, and that's beyond the scope of this course. That's something you would see in a third-year physics course maybe. So let's take a look. Let's take a look at the sort of situation we have in the diagram here, and then we're going to find the electric and magnetic force on the upper proton, and we're going to compare them sort of versus each other, right? So we're going to find the electric and magnetic force, and then we'll take their ratio to compare the sort of magnitude of the two of them. Okay. So we have our lower proton moving off in this direction. It's generating some sort of magnetic field that's been drawn in here for us. And we have our upper proton moving in this direction. There's going to be an electric field that it's going to sort of feel from, because I mean these are both positive particles, right? So we still have to consider the electric field between the two, and this is going to result in an electric force that's going to be repulsive. So it's going to be electric force in this direction. And if we think about our right hand rule for the magnetic force, if we place our right hand so that our fingers are pointing this way in the direction of the velocity of our top proton here, and we curl our fingers in the direction of the magnetic field produced by our bottom proton, our thumbs are going to point in the direction of our magnetic force that is also drawn on here. Okay, so let's do some of the calculation related to this, and I don't think I have space to keep both of these on the page, so we'll just sort of skip that and move on to the calculation. Okay, so first thing, we want to calculate the magnitude of both of these forces. So we'll start off with the magnitude of the electric force. So the force electric on this thing, thinking back to chapter 21, we know that for 2-point charges we're going to end up, well, for 2-point charges, both of which have a charge q on them, right? We're going to end up with an expression that looks like this: 4 pi epsilon naught. This is going to be q squared because it's just q times q, right? Times r squared, which is our distance between the two of these. Okay. So we could write this in terms of a vector, but we're not that interested in writing it in its vector form. Let's just note that r hat here, which is going to be the direction of our electric force, is pointing in the j hat direction. Okay, so r hat really is j hat. Okay, that's going to be our magnitude for our electric force. Let's now take a look at the magnetic force that this top particle is going to experience due to the bottom particle. We're going to start with calculating the magnetic field produced by the bottom particle moving off to the right here. So we're going to have B. Using the expression we have above, B is going to be equal to mu naught over 4 pi. And this is going to be times Q V cross r hat over r squared. Okay, and so we can kind of simplify this a little bit, because we know that our V for our bottom particle here, and this is what we're calculating, right? Remember, this V that we're looking at here, we're looking at the magnetic field produced by this bottom particle. So the V that we're looking at is the V of the bottom particle, right? So we still have an r hat that's equal to j hat, but we also have a V vector here, which is equal to the magnitude of V, and it points in the I hat direction, right? It points in the positive x direction. So let's kind of rewrite this by factoring everything out and just leaving the cross product on its own. We're going to have mu naught over 4 pi. Then we're going to have q v over r squared. And we still have our I hat cross j hat now, right? I hat from V cross j hat from R. This is going to result in k hat, right? I hat cross j hat is k hat. And so we're going to end up with a magnetic field that looks like this: mu naught over 4 pi q v over r squared k hat. Okay, that's our magnetic field. Now, because of this magnetic field, we know from the previous chapter that this moving charge, our top charge here, the one that we're interested in looking at the force acting on it, is going to experience a magnetic force. We can write down that magnetic force. That magnetic force looks like this, right? And so this is going to be minus V cross B. Why is it minus V? Well, because we've labeled this velocity up here as minus V. Now we're looking at the motion of our particle sitting in the magnetic field, right? And so we need to consider its velocity. Its velocity is minus V. Okay, so we can rewrite this a little bit. I'm going to factor out the Q here. Well, I guess really it's going to sit kind of the way it is. We're going to have minus V I hat, right? Because our V still points in the I hat direction, but now it's in the minus I hat direction. That's what the minus sign is telling us. And this is being crossed into our magnetic field, which we just calculated. I'll write it out in full here. 4 pi QV r squared k hat. Okay, and so this can all be sort of cleaned up a bunch. I just want to isolate the cross product that remains. So I'm going to factor everything out. I'm going to keep the minus sign in there, just because it kind of is going to look nicer when we're done here. So I'm going to factor out the mu naught 4 pi. We're going to have a q squared, and we're going to write these two q's. We're going to have a v squared, and we're going to have an r squared in the basement here. What remains is a minus I hat cross k hat. Okay, and so we need to think about this a little bit. Different people have different ways of remembering how these cross products work here. So the way I think about it always is I just write down, like, let's say I needed to know what this cross product was. Either I would do this determinant thing that some people do. If you don't know what I'm talking about, don't worry about that. Or quite simply, I would just write down, well, I know that I hat cross j hat equals k hat, and then every permutation of that is going to be the same, right? I can bump this k hat over to this side. Everything slides to the right one, so that means that k hat cross I hat equals j hat. And I guess I'll do the last one. I could bump the j hat over, so it'll be j hat cross k hat equals I hat. And then flipping any of these picks up a minus sign, right? So this means that j hat cross I hat equals minus k hat. This one would be telling me that I hat cross k hat equals minus j hat. And this one tells me that k hat cross j hat equals minus I hat. And then we know anytime you run into the situation where you have like an I hat cross I hat, that's just 0. J hat cross j hat, 0. K hat cross k hat, also 0. So in this case, we have I hat cross k hat. Well, I hat cross k hat is minus j hat, but I have a minus sign, so this whole thing just ends up being j hat. Okay, and so the force that's experienced by that top proton due to the magnetic field generated by the bottom proton is going to just be equal to mu naught 4 pi q squared v squared over r squared in the j hat direction. Okay, and so we have the magnetic force experienced here. We know it's in the j hat direction. We have the electric force experience, which we wrote down up here, again in the j hat direction. We didn't write it out as a vector, but we know it points in the j hat direction because r hat points j hat. And now the last part of the question wants us to compare the magnitude of the two of them. Okay, so I have some stuff worked out over here. And so let's say we look at this like this. Let's say we look at FB over FE. So the magnitude of our magnetic force experienced by the top proton due to the bottom proton over the electric force experienced by the top proton due to the bottom proton, right? So we just write out those whole expressions. We're going to end up with a mu naught q squared v squared over 4 pi r squared, and this is going to be over our expression for the electric force experienced, which is going to be q squared over 4 pi epsilon naught r squared. Okay, so we can clean this up a bunch. We can see that these, maybe I'll do it in a different color. We can see that these q's go, these 4 pi's go, these r squareds go, and we're left with mu naught v squared over 1 over epsilon naught. I can clean this up a little bit. We're going to end up with an epsilon naught mu naught times v squared. Okay, and if we remember from our discussion above, this collection of epsilon naught and mu naught is just really 1 over c squared. Okay, and so this is equal to v squared over c squared. Okay, and we said earlier that all this work that we're doing here really only applies if v is much smaller than c, right? Otherwise we have these relativistic effects. We have to take into account relativistic calculation, so we'd have to take into account special relativity, which for us here is a third-year course. And so we're not looking at that here. We're looking at small v. But if v is much, much smaller than c, obviously v squared is much, much, much smaller than c squared, right? And so this means that FB is much, much smaller than FE. And so our magnetic force, the force experienced by the top proton because of the bottom proton, is far, far less than the electric force experienced. And if we take a look at the drawing here, that's kind of how they've drawn it, right? This force, this electric force has a much longer vector here, and it's kind of trying to tell us that the force is much larger. The magnitude of that force is much larger than the magnitude of the magnetic force. Okay? So that's the example for this section. I'll leave it here, and we'll pick it up in the next video.